So this is just to give you a very, very broad summary in terms of what the different types of algorithms are. Again, each of them are very, very theoretical topics. Okay, each of these algorithms are very theoretical, but from an application perspective, just remember what these are. Okay, I want to also let you know that there is no one single rule book that tells you that which algorithm will work in what scenario. Okay, so you will have to try out in the real world scenario. If you want to implement these things, you will have to try out different algorithms, and you will have to compare the performance and see which one gives the best results. Okay, but there is no one size fits all. There is no one template that you have which will tell you that, hey, this is my data set, and for this kind of data, I will apply this algorithm. This is a common question that generally people tend to ask, but I want to clarify that you will still have to try out. It is a highly experimental domain. So if you so it's something we have been doing through our exercises also yesterday, today, some very basic academic exercises that we did. I think this is the learning that most of you would have got by now, that you try out different techniques, you try out different methods, you try out different algorithms and see which one is giving you the highest cross-validation scores. Okay, on regression on the left hand side, we started off with linear. You can be polynomials also. Okay, so on the right hand side, we have on classification, we have something called logistic, and we have something called Knight Bayes. Knight Bayes is based on the Bayes rule of probability. It is a probabilistic model. Because in classification, inherently, what are we doing? We are trying to calculate uh, what is the probability of something based on something, isn't it? If you go back to all the classification exercises we did, let's start off with yesterday, diabetes. What are we trying to do in the diabetes exercise? We are trying to predict what is the probability of diabetes given the different features of the person. So given their blood pressure, given their body mass index, given their glucose levels, what is the probability that the person will suffer from diabetes? So inherently, if you go back to the principles of probability, it's a conditional probability problem, right? So you're trying to predict the probability of something given something. And that is exactly what Knight Bayes will do. Okay, so logistic will do it a little differently. Mathematically, it does it a little differently. There's an equation that we get. So that's the theory part of it. But Knight Bayes does it a little differently. So all of these are ultimately doing classification. All these methods are ultimately doing classification, but they're doing classification in different ways, which is absolutely not, you don't need to know the theory at all for this. Okay, and even if you know the theory, it will not help you solve problems. Okay, as I told you, and as I've mentioned it multiple times, there are two very different learning paths. Okay, and something I encourage each one of you to do. So please do not waste your time going through another 6 months course and studying these theories, because solve problems, look at the applications, and based on the limited understanding we are getting here, get into problem solving. Okay, because knowing the theory will not help you solve the problems better. Okay, knowing the methods will, but knowing the theory behind the algorithms will not help you generally. Okay, so decision trees are basically applicable for both regression and classification. So decision trees are something that is useful for regression models also, classification models also. And if you're using the packages, you can use something called a decision tree regressor, and you can use something called a decision tree classifier. Random forest and gradient boosting, these are basically, if you look at these three categories especially, these are basically collections of decision trees. Okay, so at a very high level, these algorithms are effectively collections of decision trees. Okay, so we can take a particular data set and we can build a single decision tree model on the whole data, right? That's one of the ways how we can do it. So we can take a single data set and we can build one single decision tree model on the whole data. That's one of the ways how we can approach. Or what we can do is we can build multiple decision tree models across our data. Okay, and this is the idea I was trying to mention a little bit yesterday, the idea of ensemble. So these are like ensemble techniques, right? Just to clarify. So decision tree is an individual model, but if you look at these approaches, especially random forest, gradient boosting, extreme gradient boosting, extra trees, stacking and voting, these five algorithms are what we refer to as ensemble algorithms, right? And generally, they tend to perform very, very well. Result wise, these are like the gold standards. And out of all of this gradient boosting is like an absolute gold standard. So if you look at any typical competition or a real world use case where somebody is using machine learning, usually gradient boosting is a default that everybody will use. Okay, if you talk to anybody in your data science team and if you ask them that, hey, what kind of algorithms are you using? Maybe 9 out of 10 times they will tell you that we are using gradient boosting. They will not even bother to talk about logistic or decision tree or any of these other things. So 9 out of 10 times you'll hear the term gradient boosting. Okay, so at a very high level, what is happening? What is this ensemble thing? What is the meaning of this ensemble? Something I was mentioning yesterday also. So ensemble refers to a group, right? Ensemble means a crowd. It's a group. Wisdom of the crowd. So ensemble basically refers to a group. That's the way we can understand the meaning of an ensemble in a way. Right? Okay, so you have a group of models. That's the idea. Okay, you have a group of models that you're taking. So think of a scenario where there is a committee. Okay, imagine there's a committee and the committee has to take a decision whether to do something. Let's say it's a company and the company has to take a decision on funding. Okay, so it's a small startup company and they're trying to get some funding from some external stakeholders, shareholders, and let's say there's a committee that will have to take a call. The committee has to decide whether the funding should be done or the funding shouldn't be done and all that stuff, right? So the committee has to decide. Okay, so a lot of real decision making will happen in committees like this, like a lot of real world decision making will happen in committees. Because if you ask one single person to take a call, okay, if you ask one single person to take a call, then that decision might be highly biased, right? So it's very much possible that if you ask a single person to take a decision, that decision might be highly biased. Okay, so that person might decide based on their own interest. Okay, so similarly, if you have some data and if you use a single model or a single algorithm to do a prediction, that prediction can be highly biased. We might end up with issues like those skewness and those kinds of imbalances that we were discussing. So there's some mathematics around it, but generally you get the analogy, right? So you will end up getting incorrect results for certain types of data because certain models will not learn certain patterns correctly. So instead of using a single model to do a prediction, what I can do is I can instead use an ensemble model. I can use a group. So just like we have a group of 5 people in the committee. So each person will take a decision. Person one will say this. Person one will vote yes. Person two will vote yes. Person three will vote yes. Person four will vote no. Person five will vote no. Three people yes, two people no. So the model will predict yes. That's the idea. That's the idea of ensemble. And you can think of any real world decision making, like let's say jury. If you look at very important court cases that are fought, so there's a jury. There's not one single individual who decides what to do, but it's usually a jury, a group of people who decide whether the person is guilty or innocent. A jury will decide. A jury will be part of the trial. Okay, so there'll be a jury of 10 people and 9 of them say the person is guilty, one of them says the person is innocent. So we listen to all of them and we'll take an aggregate decision. That's the whole idea. And generally, it has been proven, and we have got a immense amount of data to generally see that ensemble models generally tend to work better because they are based on the philosophy of wisdom of the crowd. The crowd as a whole always does better. Okay, so each of the individual models in the ensemble are very poor. Let's say we have got, 5 different models: model one, model two, model three, model four, model five. Now, each of these individual models can be very basic. Model one is like a normal, decision tree. Model two is, let's say, logistic. Model three is naive based. You can have different models also. So each of the models are very basic models. So let's say model one says yes. Model two says diabetes yes. Model three says diabetes yes. Diabetes yes. Model five says diabetes no. Okay. So 5 models, you will individually look at their 5 predictions. Given some X, each of these models will predict 5 values independently, and then the majority vote will be taken. So the ensemble as a whole will predict yes. So this is the idea. So for classification, you will do something like a majority vote, or you can take weighted voting. And for regression, we will do something like an average or a weighted average. Because regression, we are trying to predict a numerical value, right? So this is the general concept of an ensemble. And these are all the different types of ensemble algorithms that are there, which they have variance in regression and they have variance in classification. Again, because our focus here is hands-on, our focus of these sessions are completely hands-on. When you are using this in Python, you will use random forest regressor. Similarly, there is random forest classifier, gradient boosting regressor, gradient boosting classifier. extreme gradient boosting regressor, extreme gradient boosting classifier. This is actually called XGBoost. So this is the full form, but the short form is something called XGBoost. XGBoost is also a very, very popular algorithm. Okay, it's a lot faster, it's more parallelized, and you can read about it: XGBoost regressor, XGBoost classifier. So these together, these two are two of the most popular machine learning algorithms out there. Then there are SVMs, extra tree stacking. Okay, there is something called SV, support vector classifiers, support vector regressors, SVR, SVC. You can Google out these things, but this is just to give you a very broad understanding of the different types of algorithms that you will ever come across. Okay, this is by far the most exhaustive list. There's nothing else that you will see, at least in the open source repository, because we are still using sklearn. Well, obviously, if you go to other platforms, if you go to, let's say, the same machine learning concepts are used in other places also. Okay, let's say you've got, Spark. If you know Apache Spark, Spark has something called Spark MLlib. So Spark MLlib is the native, machine learning library in Apache Spark. Okay, so yeah, so different languages might have their own, different frameworks will have their own machine learning algorithms built into it, but the core concepts are still the same. Okay, if you have decision tree here, you will have a decision tree somewhere else. If you have random forest here, you will have an ensemble or random forest somewhere else. The core ideas are the same. Well, you will, if you go to more paid platforms or other platforms, you will see some different variants of algorithms. Okay, like for example, if I go to Azure, Azure has different thing, something else. It doesn't exactly have something called a random forest. Okay, it has some other term, but the idea is still the same. If you go to AWS, AWS has something called AWS SageMaker. Inside SageMaker, they don't have something called, let's say extra trees classifier, but they have something else. They have some other similar algorithms that are again proprietary to AWS SageMaker.